Hi everyone, my name is Arnau Blanco, and for today's video I'll be talking about the basics of NifTI visualization using Matlab, and everything I will do in this video will be published on my GitHub page, so you can check that out. And if you have any questions or doubts, you can just type them in the comment section below, okay? So let's see. So the first thing I'm going to talk about is the things you're going to need for this project. Obviously you need Matlab, otherwise it would be impossible to do this. Then you need the Image Processing Toolbox, because we're going to use some functions that need that toolbox. And then you need an anatomical image and a functional image in the NifTI formats, okay? The NifTI format can be .nii or .nii.gz, okay? Both formats are okay for the import, okay? All right, so you can get the anatomical and the functional image from this open source website, where you can find basically a lot of data sets which are really good. You can just type here, for example, fMRI, and you'll find tons of examples of that you can play with, okay? For example, there is this one from Yale University, I think. Yeah, whatever. Well, you can find a lot of things that you can work with, and that will be very useful for you to work with real life examples, not real life data. Okay, so once you have this, I'm gonna point out something that is quite important, I think, which is this. Okay, so this is an anatomical image. An anatomical image, when we import it, will be an array. In particular, it will be a 3D array. Okay, we will have the width, the height, and then the depth. Okay, so it will be 3 dimensions. Whereas in the functional image, we will have 4 dimensions. We will have the height, the width, the depth, and then time, because it changes over time. Okay, so this is very important, and we will see that in a minute now. Okay, so let's start coding. This is the outline of the code. Okay, first of all, I'm just gonna use clear all and close all to clear the variables or to close the figures. It'll be useful later when we code. Okay, and the first thing I'm gonna code is the data retrieval part of the anatomical image. Okay, so the first thing we're gonna do is to write the path of my anatomical image, which is this one here. Okay, and then I'm gonna load it. To load it, we're gonna use the NifTI read function. Okay, and then I'm just gonna type the path. It's this function here, NifTI read function. Okay, read NifTI image. Okay, and you just specify the file name. Okay, so when I do this, if I run this section, I will have, as expected, a 3D array with 3 dimensions, which are these ones. Okay, and now before we do the visualization, what I want to say is that when we visualize the brain, we can do it in 2 ways. We can do it in a 3D manner. We can see the 3 dimensions, the width, the height and the depth, or we can see slices. Okay, we can see different views of the brain. Okay, we'll see that in a minute. So we can do it in 3. We can see it in 3 dimensions or in 2 dimensions. Okay, if we want to see it in 2 dimensions, we need to normalize the data, because the data, let me show it to you. The data, I'm gonna say, yeah, the 100 is okay. If I visualize this aux, yeah, here, we can see that the values don't go from 0 to 255. And why am I saying 255? Well, because the standard for RGB the values for the RGB color wheel go from 0 to 255. We have 3 channels and they all go from 0 to 255. In this case, we have a grayscale image, so we're going to only have one channel, which is totally fine, but the values have to go from 0 to 255, or since we're going to use the imShow function, the values have to go from 0 to 1, okay? So if we just normalize it so that the voxels in the anatomical image go from 0 to 1, we will be able to visualize the image with no problem, okay? Okay, so now that I have just pointed that out, let's visualize the image, okay? So the first thing I'm gonna do is implement the function that I didn't show to you, this function here, which is the function that we use to normalize a feature, okay, in this case a voxel or a set of voxels. We have our voxel here which is x, then we have the minimum value of the whole image, okay, so if we have the 3D image, we take the minimum of the whole image and then divide it by the maximum of the whole image minus the minimum of the whole image, okay? So let's try to implement that in code. So I'm gonna use, to calculate the maximum, Dmax function, okay, which is this one. And to calculate the maximum of the whole array, I'm going to use this expression here, okay. In my case, my array is VA. And for the minimum, I'm going to do exactly the same thing, okay? But in this case, I'm gonna type min, which is gonna do the same thing, but for the minimum, okay? So now let's implement the formula. I'm gonna call this VA prime, and the formula is this one, as we saw. And notice here that I'm dividing element wise, okay, that's what I want. And then I'm going to create this variable called dim, which is going to basically save the dimensions of VA or V prime. Is the same thing. They will have the same dimensions, okay? This will be useful later. We'll see that in a minute. Okay, so now that I have this, we can see that the maximum is it's a scalar and the minimum is another scalar, so that's fine. So now we can visualize, first of all, I'm going to do the 3D visualization. For the 3D visualization, I'm going to use the function volShow, okay, which basically displays a volume. So for the volShow, you don't need to normalize the data, okay? We can just put here the VA, okay, it's totally fine, and it will show me the brain in 3D, which is really cool in my opinion, really cool. We can see that pretty well, okay, and actually I'm going to show you how it doesn't change at all if I put the normalized data, because volShow normalizes the data automatically. So if it detects that this is normalized, it doesn't normalize it. So yes, it doesn't matter really if you normalize it or not. But for the 2D visualization, we do need to normalize the data, okay? So the first thing I'm gonna do here is basically define the slices of the volume, okay? Okay, so what do I mean by the slices of the volume? Well, we're going to visualize 3 different views of the brain. In particular, we're going to view the frontal view, the horizontal view, and the sagittal view, okay? So in each of these views, we are fixing one dimension because we have a 3D volume and we want to project this 3D volume onto a 2D plane. So we have to fix one dimension, okay? So in the case of the frontal plane, we're going to fix the depth because, as you can see, Z doesn't change here. In the case of the horizontal plane, we're going to fix y, and in the case of and in the case of sagittal, we're going to fix x. Okay, so let's try to implement that. I'm gonna say that the slice for x will be, let's say, more or less half of the volume. The same thing for slice of y, and for z the same thing. Okay, so as we said, for the frontal view, we're going to fix. In the frontal view, we were fixing what? We were fixing z. So here I'm gonna have x and y with no fixing, and then in the third dimension I'm going to fix it to 100. Okay, and this will be the same for the rest of the views. Sagittal and horizontal. In the sagittal view, I'm fixing x, as we said. Yes, x. I'm fixing x. And in the horizontal, I'm fixing y. So I'm gonna fix y here. Okay. So we can see that we have the variables here, but we have one problem. The problem is that in the case of sagittal and horizontal, we don't have a 2x2 array, and that's what we want to visualize the brain, because it will be an image. So for the case of frontal, we don't have to do anything. Actually, I'm going to show you what it will look. So it'll look like this with no problem. But if I try to do imshow of horizontal, then it pops up an error. Okay, so I need to reshape sagittal and horizontal, and the dimensions that this will have will be the second dimension, that is this one here, 256, and the third one. Okay, and in the case of horizontal, I'm going to have the first and the third one. Okay, reshape, and that's it. And now we can just visualize the image. I'm going to copy the code that I have. Okay, there was a typo here. But we still have a problem here, which is the fact that the image is rotated. So we can rotate this with the imRotate function. Okay, so let's do that, imRotate. And here we specify the degrees. So let's say 90. No, it's minus 90. Okay, frontal, and the same thing for the rest. Okay, perfect. So this is what we want. Okay, so we have visualized the anatomical image in 3D with vol show and in 2D with imshow. Okay, Okay, so let's now move on to the functional image. Okay, and for the data retrieval, we're going to basically copy and paste the code that we have already because it's the same thing. But in this case, we're going to see now this is in this code, we'll see that there is something different. And as we said, the functional image, it will be a 4D array, okay? So actually, if I run this, we'll see that VF is a 4D array, okay? So we need to, in order to visualize this in a 3D space, we need to calculate the mean, okay? And the mean will be in the fourth dimension, which is time. So we're going to get rid of time by taking all the volumes of this fourth dimension, and we're going to calculate the average, okay? We could take, for example, the first volume or another volume, but we decided to take the average, okay? So to do this, we calculate the average by using the min function, okay? So now we can normalize the data again, as we did before. Perfect. Okay, so what we have here is a 3-dimensional array, which is what we want. And for the data visualization, we can basically copy and paste again what we have, because it'll be the same thing. Okay, make sure that you change all the variables correctly, because otherwise you will get some errors, okay? Okay, so here we can see the 3 images again, but in this case, we need to rotate this again, okay? In this case, we need to change this to 90, 90, and 90. Yes, that's how it should be, okay? So we can see it's the same thing. Okay, and for the 3D, the problem with the 3D is that it also takes the space where there is nothing, okay? It takes that as black, and then it visualizes that, okay? We can see this as a sort of box, okay? But we can see that still it visualizes the image, okay? Okay, so what if we want to visualize the 4th dimension as well, okay? There is one way we can do this, and it's normally the way we're gonna visualize it is by means of a plot, okay? So imagine we take one voxel, let's say we take voxel 40, 30, and 25, okay? And we want to visualize this so this voxel will be X, Y, Z, and then time, we're not fixing time here. And we have that voxel array because it has 1 dimension, 1 dimension, 1 dimension, and then 222, which is the number of time points. So we need to reshape this so that we have we're going to have this, okay? We're going to have a voxel that has 222 values. But what we want is this shape, okay? So the way we're going to plot this is like this, okay? And then I'm also gonna add some labels and a title. Okay, So we can visualize the signal here. Okay, this will be the voltage of that voxel and then the time points. Here, for example, we see that there is a glitch at the beginning of the signal, so we can get rid of that by just, for example, saying that we want to start at 4, and here we start at 4 and we end normally. So here we can see that we get rid of that, and we can see the signal with no problem, and then we can work with this. Okay, we can just extract some data, some statistic parameters, whatever we want, and it's very easy to work with. Okay guys, thank you very much for your attention. If you have any questions, as I said, just comment down below. I hope it has been clear. And yeah, if you like this video, thumbs up this video, and I'll see you in the next video. Okay, bye, thanks.